if we have a function with 2 inputs and 3 outputs, then the best visualization here is as a parametric surface. So when we see these, we can think we've got our outputs are in 3-dimensional space, right? So, and then we have 2 inputs that we can possibly change. So we have two freedoms in 3-dimensional space. This must be some kind of parametric surface. The parameters are the 2 inputs. As an example, suppose we have a function that looks like this. R of u and v is equal to u cosine v, u sine v, and u squared. So we're thinking that given our 2 inputs u and v, we have 3 outputs, which we'll think of as a location in 3-dimensional space, an x, y, and z coordinate. Okay, now for this parametric surface, I notice that if you take x squared plus y squared, you have u squared cosine squared v plus u squared sine squared v, and that's equal to u squared, because we have u squared, if we factor it out, we have u squared times cosine squared plus sine squared v, but cosine squared plus sine squared is 1. And that's equal to z, so, right, because z is u squared. So we can see this surface is actually a paraboloid. It's z equals y squared. So we can visualize this surface. This is our x-axis, our y-axis, and our z-axis. If we freeze x at 0, we have a parabola opening up, right, in the yz plane. If we freeze y at 0, we have a parabola opening up in the xz plane. And if we freeze z at a positive value, then we get circles, right? The bigger z is, the bigger the radius of the circle. Okay, so the radius is increasing as the square root of z, so it's kind of bent up like this. We have this parabola. So this is really just a parametrization of that particular surface. You could think for each location in the UV plane, right, each location here is being turned into a point over here on this elliptical paraboloid. So this is, remember the name here. If you slice it in most directions, it's a parabola, so the name is paraboloid. And if you slice it in one direction, it's elliptic. So we've got an elliptic paraboloid, okay, as the surface. Now, an example of a linear function of this type might be something like u and v and u plus v, right? Which we could also write as a matrix here. We have u and we have v and we have u plus v. We could think of that as a matrix, a 3x2 matrix, because there are 3 outputs and 2 inputs, times a 2x1, our 2 inputs u and v. Let's see, our first output is 1 times u and 0 times v. Our second output is 0 times u and 1 times v. And our third output is 1 times u and 1 times v. So there's an example of writing it as a matrix times a vector of inputs. So we have this vector of inputs uv. The linear ones, of course, can always be represented as a matrix times a vector of inputs. R of u and v, that's an example. Now if we wanted to think about what this is, we could notice that if this is our x and this is our y and this is our z, then z is equal to x plus y, which we recognize as the equation of a plane. If you wanted to get the normal of that plane, so you could write it this way, x plus y minus z equals 0. The normal to that plane are the coefficients of the variables, 1 times x, 1 times y, and negative 1 times z. So we have a plane through the origin here, and its normal goes out 1, over 1, and down 1. So the normal looks something like this, and we have the plane that is perpendicular to that normal. Another way to visualize this plane would be, once we have the Cartesian equation here, we could say, well, If we set x equal to 0, we have the line z equals y, right? And if we set y equals 0, we have the line z equals x. This is a line in the xz plane. And then we could imagine all the points that you can create like that with that plane.